All right, so
Okay.
Oh, you're good. Oh, wonderful. The long-awaited Hadas talk.
There you go.
So it's my pleasure to introduce Hadas Kress-Gazit. She is a professor at Cornell University. She's been there for about 5 or so years, depending upon how you count. I've known her for a long time. You know, if you look at her little bio, she writes about how she won the Career Award in 2010, and then recently the DARPA Young Investigator Award, which is pretty impressive to win. In fact, yeah, it's pretty good. But the thing that she didn't include on her bio was she was actually nominated for Best Paper at IROS with our very own David Connor back in 2007. And so I think winning an award with Dave Connor and getting the Young Investigator Award from DARPA just means you gotta be great. So without further ado, I'll give you the DOS and let's ask her lots of questions and make her earn her time here.
Exactly. All right, thanks, Howie. Thank you very much for inviting me and hosting me. This has been a very, very, very enjoyable day. So I want to give you a feel for what we do in my group. So it's going to be more of a breadth type talk. And I really want to give you the taste of what we're doing. And again, I like interactive talks. It's more than me just lecturing at you. So if you have any questions along the way, please interrupt. All right, so my title of my talk is High Level of Verifiable Robotics. I have 3 types of fonts there on purpose. And the reason I have 3 different fonts is these are 3 different aspects that we deal with in my group. And I'll clarify that. Sorry. So this is a now humanoid robot. I'm sure some of you have these walking around here. Imagine I want to ask it to go pick up red balls in my lab. So we had an undergrad project to do exactly that. So it goes and picks up red balls in the lab. Great. Then what I want to do is I want to put this now on a Segway platform and have it to go deliver letters in the office building. Another, kind of not too, it's a fairly cool task, but I can do that. How do we usually do these things? How do we usually perform these types of actions or types of tasks? So usually what happens is someone has an idea of a specification of what they want the robot to do. But what they actually do, they sit down and they write an implementation. They write the code, be it in ROS and any type of robot software that you want. You sit down and you write the code. And then what do? You test. First time you run it, usually doesn't work out. Second time you run it, you found some of the bugs, still doesn't work. After a few times that you run it, you're happy because it works, and you're kind of fairly confident that it will do what it's supposed to do. Are you guaranteed that it will work? No. Are you likely to work? Yeah, under certain conditions. So if you suddenly move the robot to a totally different environment, is that going to work yet? You're not quite sure. But really the paradigm is write an implementation and test. Write an implementation and test. Now what happens if you want to, I wasn't sure whether it's going to crash on me or not. What happens if you want to now have the robot pick up balls in the lab, and 5 minutes later, put it on the Segway and have it go deliver letters in Upson. And this is just kind of to show that we did it. So now the idea of writing implementation, testing, writing implementation, debugging, testing, that no longer works, right? Because these things take time, they're error prone. Am I really guaranteed to have any guarantees about the behavior? It's not quite clear. So really what I'm trying to advocate, and what my research group really tries to push, is the idea of changing the paradigm. So instead of talking about an implementation, having someone write the code to actually do the work and then test it, move it to a paradigm in which you talk about the specification, what you want the robot to do and not how it should be done, and then have some machinery, some algorithmic machinery in the middle that automatically creates a controller that's correct by construction. So I have guarantees for the behavior. Now the reason I have an asterisk there is sometimes I might ask the robot to do something that it can't. It can't do it because it's logically inconsistent. It can't do it because it's physically inconsistent with the dynamics. It can't do it because it's very likely to fail because we have some uncertainty. So whenever those situations happen, what I want to do is I want to provide feedback to the user saying, what, I can't do this because X, Y, Z. So the idea is really reason about the specification. Have a novice user, non-PhD in engineering, robotics, whatever, so computer science, tell the robot what it should be doing, and then have everything else be a black box that's guaranteed to be correct. So kind of to tie this back to the title of my talk, the high level is what are these specifications? And I'll talk a little bit about that. The verifiable part is really, what is this machinery and how does it apply to robotics? What are the specific challenges and what can we say and what can we do with the idea of verifying robots, or verifying robot behavior. I'm going to start with talking about the verifiable part, about this black box, what's in this black box. And then I'll talk a little bit about the high-level stuff, in which we're interested in more connections to language. But that's kind of, we'll talk a little bit about that, but not a lot. All right, so let me kind of put this in perspective a little bit. Let me give you, and throughout this talk, I'm going to give you very simple tasks, so it's easy to visualize what's going on. So let me give you one task. The task is, this is my workspace. This is my abstract. This is just a picture of my workspace. This is the actual workspace in the lab. We have a Vicon system that allows us to localize. It's kind of fun. The task is to patrol the corners. So those 4 corners that have a different color, those are the corners. If you find a missing item, call the manager. So the robot is able to detect, can abstract, using whatever vision, whatever type of sensor it has, we can abstract the notion of what a missing item is, and it can detect whether something is missing or not. It's able to call a manager. And avoid aisles with spill. The aisles are the 2 regions that have the arrows in them. So the 2 long regions in the middle there. I can't actually reach there. Okay, so this is my task. It's very simple. The thing I want to emphasize here, this is a reactive task. The robot will behave differently depending on what happens in the workspace. So if it sees a missing item, it will stop and call the manager. In our case, calling the manager is waving. If it doesn't see a missing item, it will just patrol forever. So it's really, it's reactive to the environment. So let me just do this. So let me show you this task being executed on the robot. So this is times 8, so then now does not walk very fast. It found a missing item. I don't know if you could hear that. It said, I found a missing item. So it's waving. The manager, in this case Cameron, who used to be my student, told it to fine, I took that away. If you'll notice, the sensing is really reduced to using fiducial, so using this radial barcodes, and the now's vision system. So in this case, that's a spill. So it has a radial barcode that denotes a spill. It's continuing to patrol, so it reacted to the spill. It didn't go into the area with the spill, and it went all the way around. Okay, so it detected another spill, and it reacted the way we asked it to react. Okay, so I want to talk a little bit about, the majority of the talk is going to be about the verifiable. What is this algorithmic box that we have, and how do we apply this, and what does it mean when we talk about robotics? So let me talk a little bit about that, but before I go into the details, let me give you the approach in a nutshell. So really, the 60-second version of what's going on here. So we have a continuous problem. We have a robot moving around an environment, detecting things and reacting to them. It's a continuous problem. The first thing we want to do is we want to abstract it into a discrete problem. The way we do that is we take the things of interest and we abstract them using propositions. So propositions could either be true or false. So for example, I see an item that could be true or false. It's kind of a discrete event that I can detect. And then or the motion of the robot I can abstract it by partitioning the workspace into pieces. So I can say, I don't know what the seminar room is, but Hadas in seminar room is currently true, but it might be false later. And then I capture the specification using linear temporal logic. And again, this is I have people here that's what they do. So let me be very, very non-formal about what linear temporal logic is. The idea is you have the Boolean connectives, you have and or, you have the propositions, you have and or not. Then you have some temporal modalities. So you have next, always, eventually, and until. So now you can reason about things that evolve with time. So for example, I can pose a formula that says Hadas always in, or it's always true that Hadas in seminar room. That formula is false because eventually it won't be in here. But the formula Hadas eventually, or eventually Hadas in the seminar room is true because I currently am in the seminar room. So that formula is true. So I can reason, and we can capture a lot of reactive tasks this way, mainly using implications. If you see this, then eventually do that, and so on.
Is it the weak or strong or until?
So we're actually not using the until. For the fragment we were looking at is only the always and the always eventually, but this is usually denoted as a strong until. But again, for the synthesis that we're using, we're not really using the until operator. Once we have that abstraction, now we've captured our task using this logic, representing the task using the logic, representing the system. We try to find a provably correct discrete controller. So we find a state machine such that every execution of the state machine satisfies the original task, or to be more exact, satisfies the original formula, if one exists. So if I cannot find a state machine that every execution of it will satisfy my task, I'm going to tell you, can't do it. All right? So originally, this is kind of started from my PhD work, in which we really literally said, can do it. But now you'll see we have a little more intelligent responses to why I can't do it. Once I solve this, I have a discrete controller. And now the question is, how do I take this discrete controller and continuously implement it back to the physical system? Because now we're talking about trajectories. Now we're talking about velocities, waving commands, or whatever commands you would like to do. So the question of how to continuously implement. And I've highlighted in blue the main challenges of this approach. What is the right abstraction, right? So if I have a robot moving in 2D, I can kind of tell what the abstraction is. It's not very difficult. I can partition the workspace and all that. But I've been talking to some of you today, and really, for a manipulation task, what is the right abstraction? There are a lot of questions there, because I can think about Vox lines in the space, but that's not quite the right abstraction. It doesn't scale. It's not very intuitive, and so on. How do we create the provably correct controller, but now provably correct with respect to the discrete specification? We know how to do that. But how do we incorporate the fact that we have a continuous system underneath, and what does it mean provably correct with that? And how do we continuously implement? Have a discrete entity. What does it mean? What are the semantics of this continuous execution? And I'm going to talk about some things that we've done and some things that I'm not going to talk about today. So this has been kind of more in this is kind of other people's groups, in kind of definitely in the robotics community of interest, the hybrid systems community, the more formal methods community are looking into these things, and it's kind of exciting. So I want to talk to you about what happens when we try to apply the formal methods for robotics. So this is, you saw already this robot. So let me start talking about the fact that we have a human controlling a robot. So this is the task that I just showed you a video of the robot doing. I lied. It's not actually doing this task. This task is impossible. Any ideas why this is impossible? Well, I'm asking you to patrol the corners. Yeah? Any suggestions? I heard something.
It's like both aisles are spoiled and we cannot avoid.
Great. I have a contradiction. I could create a contradiction here. So I want to patrol all the corners, but I can't go through aisles with spills. What happens if I have spills in both aisles? So what you saw is that the robot preferred to just give up, right? So it's not going to violate the safety of not going through an aisle with a spill. But this is not listed here. Right? If I was to give this specification to a programmer, most likely they would choose what is more important for them, or not. Or maybe they'd come back and say, I don't know what to do here. But really, I think in many cases, someone will put their preference, their own personal preference here. But there's no preference here. So what happened when we ran this? Basically, we didn't get a controller. We said, we can't do this. This was before we actually had the tools to explain why we can't do this, which I'll talk about in a second. But then we figured out, OK, you know what? There's a contradiction here. We are changing the specification to have a preference. It's more important for me to not go through the aisles with spills. Okay, and that's the video that you saw. So generalizing a little bit, I can think about different problems in my specifications. I can think about a specification that's unsatisfiable, which means that the robot can't do it. For example, if I say, start in deck, always stay there, go to the kitchen. Logically, I can't do that. I can't be in two places at the same time. I can't stay here all the time and go somewhere else. That's logically inconsistent. These tend to be things that are easier to find. I mean, not always, but things that are easier to find. A different thing is these are reactive tasks. So this is, I want to react to what the environment is doing. So now I can think about specifications that are unrealizable. This means that the environment, which I'm treating as an adversary, so this is definitely a worst case approach, the environment can do something to make me fail. The environment can also make me, can allow me to do my task, but there is at least one behavior for the environment that will make me fail. An example for that is start in the deck. If you see a person, stay there, go to kitchen. If I never see a person, no problem. I can definitely do this. If there's a person constantly next to me, I cannot stay there always and go to the kitchen. So there's an environment that will make me fail, and this is unrealizable. Okay, so there's something that, in some situations, I'll be able to do it. In some situations, I, being the robot, will not be able to do this. When we talk about problem in specifications, these are kind of the things that make sense, right? So I can't generate a controller because either you're asking me to do something that's impossible, or you're asking me to do something that the environment can make me fail. But we've noticed that there's another type of problematic specifications, and I'm glossing over exact structure of the LTL formula that we're looking at, so there is some structure. But conceptually what we have a formula of this structure. It has substructure as well, so it's a subset of LTL. Phi E is some assumptions about the environment, implies phi S. So this is an implication, so this formula holds true if this is true, meaning the robot is doing what it's supposed to do, or if this is false. So if this is false, this whole thing is true, and then the robot doesn't need to do anything because this whole thing is satisfied. So what would happen is if we wrote always person and not person, so this is kind of in a structured language representation, I'm assuming that the environment always sees, is always detecting a person and not detecting a person. So obviously this is an impossible environment because it's either or, can't do both at the same time. So in this case, what we would get would be a trivial solution. What we would get is we would run the synthesis algorithm, we'd get a controller, we'd run the robot, and the robot would stand there. And then we'd go and look at the controller, and we'll see there's a one state controller. It doesn't have to do anything because you're already failing. The environment is already failing. So this is another thing that we want to detect in the specification, these trivial solutions. So this whole line of research started, and this is mainly the research of the work of Vasuraman, who was my student, and now she's a postdoc at Caltech. This main line of research to be able to provide feedback as to what's the problem started from a lot of frustration as a grad student trying to run a specification that just would not synthesize, and I could not for the life of me figure out why. So what we're able to do now, we are able to provide minimal explanations. It's not a unique minimal explanation, but it's a minimal explanation to what's the problem with the specification. And to be able to provide a minimal, what we're using is the notion of unsatisfiable cores. So some of you may know, and some of you may not know the whole SAT problem. So if you have a propositional formula, figure out whether there's a satisfying assignment to the propositions to see whether the formula evaluates as true. That's the SAT problem. It's a hard problem, but their SAT solvers right now are pretty amazing. They can solve, I think, millions of variables in kind of in a reasonable amount of time. So what they're able to do is to provide unsat cores, which basically means a subset of the formula that causes the problem if it's unsatisfiable. Now we're using LTL, which is not quite propositional, but what we're doing is we're unrolling the LTL formula to a finite depth, and thereby creating a propositional formula. And then when we find the unsat cores, what we can do is we can map it back to the original LTL and back to the language that we were using. So I'll talk a little bit about the language we're using a little bit later. So that's the idea. So we're able to use these techniques to show you, I can give you a big specification. Using these techniques, I can show you, what, the problem is in this area. So this is the example. This is a long specification. This is a different task. It doesn't really matter what the sentences are. This is in the structured English, which I'll talk about in a second, which is not pretty, but better than writing logic. And really what we figure out the specification was unsynthesizable, and the problem is these 3 sentences. Everything else is fine. Fix these 3 sentences. Okay, so that's one of the things we were able to do, provide a minimal explanation, or map it back to the original specification to figure out what's going on wrong. The other thing that, so we're able to do that. Sometimes this is not quite enough. Sometimes this will still tell you that, will still give you kind of a larger subset, especially for unrealizable cases. If there's something the environment can do to make you fail, it's sometimes hard to figure that out. So another thing that we've done, and this is inspired by some work in the formal methods community for kind of hardware design tools, is, what? You think you can do this? I'm telling you can't. You want to understand why you can't? You play the robot. We're gonna give you a simulation screen. You play the robot. The tool, me. I'm gonna play the environment. I'm gonna show you how I'm gonna make you fail. So I'm gonna show you a fairly simple example. So this is the example that I want to show you. This is our toolbox, little mop. I'll show you in a second. The specification is very simple. This is some of the natural language work that we've been doing. So the specification is follow me, don't go into the kitchen. I can't do this because if the person goes into the kitchen, I have a contradiction, right? I can't follow the person and not go into the kitchen. So this is very simple, again, to illustrate these ideas. But what we're doing is, if you didn't understand why it can't be done, We're going to allow you to play against the environment. So this is synthesized, it's unrealizable. This is the parse tree, I'm not going to talk about that. This is the kind of going from the natural language to the logic. It's highlighting the problems. This is this, let me just stop this for a second. This is the simulation. So this is my map. It's telling me where the robot is the white dot. It's telling me where the person you're following is in there. And you're trying to match that. Now, you choose where you're going to go next. And if you choose something that's illegal, I'm going to not let you do that and tell you why it's illegal. For example, you'll see in a second, it's going to try to move to a room that's not adjacent. So I can't just fly over regions. So that's impossible. It's a topological constraint. And it won't let me go into the kitchen. Let me just continue this. So I can choose to go different places. Now I'm going to try to go here. It's going to tell me invalid move because of topological constraints. So I can't do that. Now I'm going to move there. I'm going to try to go into the kitchen. Invalid move because he told me not to go into the kitchen. Right? So then I can start seeing what's going on there. And the more I play, the more I can figure out what the environment strategy is. Because the environment strategy might be an infinite strategy to make me fail. So this will let me kind of figure out what's going on. So this is one aspect of the fact that this is just basically dealing with the specification themselves. Did you ask me to do something that I cannot guarantee I'll be able to do at the discrete level, at the logical level? Sometimes, and you'll see an example, and this is goes again with a lot of some of the people I've been talking to today. We have a person controlling a robot, so there are certain expectations about what the things should look like. So, for example, let's say the task is patrol the yellow areas. Don't go through so I have these yellow areas, R1 through R4. I have a region D1. Let's assume it's abstracting a door. And the door can be open or closed. I'm not controlling that. The environment is controlling that. My only assumption is that infinitely often, my door will be open. So I'll be able to go through there. So this is the task, and this is the trajectory we get. So we synthesize a controller. We get a controller that can be translated into continuous motion. And I look at this and I say, you know what, this is correct, but this looks weird. Why would I go all the way through H3? Why am I going all the way around? This makes no sense. Now, it does make sense if you think about what it's optimizing, but it's looking at the discrete problem and not the continuous problem. So we're calling this reasonability. So maybe I should call this more legibility, kind of in the Anka Dragon type terminology. But the problem here is that if the robot starts here and it starts moving in this direction, you would stop the robot because it's doing something that doesn't make sense. It doesn't look like it should be doing this thing. So the question is, how do we change it? But it's correct, right? So it is doing what it's supposed to be doing. Now, the question is, how do we incorporate some notion of cost to make trajectories that are still correct, but more reasonable? So to do that, we talked about, and there's been work on incorporating continuous metrics, so putting weights on transitions and optimizing on that. We did something similar. Now we've defined two things. We've defined a continuous metric, so I can, and this can be anything. It can be distance, can be energy, can be curvature, whatever continuous metric you're interested in. I can define how much a transition costs. But another thing we're defining is how many times do I have to wait for the environment to make me be able to do my task. For example, the door. How many times to figure out, to complete my task, how many times do I have to wait for something, for the door to open, for example? And now we have this tuple. We have a tuple that contains two costs. And now I'm going to optimize based on your preferences. You tell me what's more important to you. Is the continuous metric more important to you? I'm going to optimize on that. Is the discrete, is the delay cost, is the waiting cost more important to you? I'm going to optimize on that. As long as you give me some partial ordering on these pairs, then I can optimize on that and get different behaviors. So once we run that, we get this blue trajectory. So what do you think I was optimizing on? So I have two costs. I have the continuous cost and I have the delay cost, the waiting cost. What do you think I was optimizing for? The waiting. How can you tell that I'm doing the waiting? Because I'm never going through the door. So I'm totally independent of the environment. I don't care if the door is closed or open. I am able to do what I want to do. I do not have to wait for the environment. What's the price? The price is the trajectories. It takes me longer to go between regions 1 and region 2, as opposed if I was just to go in circles. in this environment. So now I can choose whatever I want to do with this. So whatever kind of cross-metric or the tuples that I'm looking at here. Okay, so this type of work, I mean, we've been looking at this kind of lately. Let me show you another kind of quick video. So I talked about just the human aspect. So we have specifications that might be wrong or might be not guaranteed. We talked about kind of the behavior that's correct but not quite right in terms of the human. Now let's talk about what happens when we're controlling a robot. So again, this is the same task. We have those aisles. It's detecting, it's supposed to detect an aisle with a spill and not go there. And this is what we had to do. So, I'm at the Robotics Institute, so this is cool. So I'm sure most of you have seen robots behaving not quite as they were supposed to behave. But here I'm talking to you about verifiable robotics. I'm talking to you about verifying robots, and I'm showing you this, right? So what am I talking about? So what happened here? Well, now the humanoid that now has a camera. It actually has a camera here and a camera here, and it was scanning. It was scanning too fast. It just never locked onto that to the QR tag. It didn't see it. So as far as the robot's concerned, it was doing the right thing. There was no spill. It was going about its task. As far as me looking at this and saying, you know what, there's a spill there. Why is it not stopping? Why did Cameron have to jump in and kind of grab the robot before it crashed into the cone? So the question is, we have sensors. I'm abstracting them away, but they're not going to be perfect. I can abstract, that's fine, but I'm going to get false positives and false negatives. Actuation, I can abstract. Is it always going to get, when I'm applying an action, will I definitely get the action I'm expecting, the result I'm expecting? Not quite. So the question is, what do you do when you have these uncertainties, when you have these errors in play? So this is what we did. What we said, we took, first step we took was to take a kind of analysis question, and treat this as an analysis question. So let's assume I'm going to generate a controller, assuming everything is perfect. So everything is perfect, of course, in the robotics world. I synthesize a controller. I get a controller for that, assuming my specification is OK, of course. And now what I'm going to do, I'm going to compose this controller with models of my environment. So how likely are things to happen? With a model of my sensor, how likely is it to give me the wrong answer? So what's the probability of false positives, false negatives? And some actuation uncertainty. If I tell you to go forward, how likely are you to go to the right? And I'm going to take all this and compose this into one Markov chain or MD or Markov decision process, depending on the situation. And what I'm going to model check this. And what I'm going to do, I'm going to take a probabilistic model checker, and there are things available in the community. And now I can check how likely it is for me to satisfy my specification, and usually over a finite duration, so in 50 steps and 100 steps. So we're able to, I give you a specification, and then I can actually model check different specification. It doesn't even have to be my original specification. I just want to see how likely is the robot to do A, B, and C, or how likely is it to not collide with a car. That's the first thing we did. The second thing that we did is we said, you know what? This is kind of the same idea. I can still analyze, but now let me take this analysis, and instead of giving you a number, 80%, you're likely to succeed in your task. Now let me give you suggestions for how to change your task so that you're more likely to succeed. So we've broken this up into kind of 4 different types of revisions. One revision is to add safety specifications. So maybe my task is to go out of this room into the hallway. There are 2 doors. So initially I don't restrict anything. I can take any door. But maybe it's very unlikely for me to be able to go out that door. So now I'm just going to restrict it. I'm just going to say never use that door. So now my controller will definitely take me to the only possibility. And then I'm going to get a controller that's more likely to succeed by restricting the robot more. I could restrict initial conditions. So the nice thing about this type of synthesis, of reactive synthesis, I don't have to have a single initial condition. In many cases, I don't even know what my initial condition is. So I'm planning for multiple initial conditions. But if I say, if I start out behind this podium, I'm more likely to crash into this. So you know what? If you just start in the middle, kind of this big space here, you're more likely to succeed. So I can tell you that. Just don't start over there. You're much more likely to succeed. That's the idea of restricting the initial conditions. What happens if I have, someone gave me $1,000 to improve my robot? I can go buy, one more really, really awesome sensor. Where should I put the money in? Where should I invest that in? What is the sensor that's causing task to fail the most? What is the bottleneck in terms of sensing? So this will give me some intuition in terms of, you know what, if you need to fix anything, fix this. If you give me this more accurate, I'm way more likely to succeed. And the final thing, and this is something that we are able to provide this, but this is not, I don't think philosophically this is the right thing to do. But you know what, if you tell me I need to go here, I need to go to Matt's office, and I need to go to Howie's office, but getting to Howie's office is tricky because of all those corridors and all that, maybe if you remove that from your task, you're much more likely to succeed. So that's the goal or the liveness that makes me fail the most. So I can give you that information too. So the idea is not, so there's work in the community that try to find the control that's the best, that will be most successful, and those are great pieces of work. Here what we're trying to do is not change anything about the task, but rather tell you, you know what, this will make it better, this will make it better. Now you choose, you tell me what is still consistent with what you want to happen. And what we're working on right now, and this is Ben's work, and he's going to be graduating in May, is incorporating this, using the kind of the cost ideas that we had before, putting those costs into synthesizing the best controller. So to some extent, we're able to generate a controller right now, and then we can analyze and then start adding revisions. But maybe there's a way to, but what we want to do is kind of synthesize the best one, and then start providing other revisions beyond those. So that's the idea of kind of incorporating uncertainty. And this is a big question, right? Because these things are not definitely, so the pushback I get the most, and depending on how long you've known me or not, or known of this body of work in the community, is you can't verify robots, right? So I can't say a robot will 100% work. And there's this cool video of Asimo walking up the Honda humanoid, walking upstairs, something breaking, and it kind of falls on its back and kind of falls down the stairs. I can't guarantee a motor won't break, right? But having more and more guarantees and being able to say more and more things about these systems is a very important thing, just to be able to deploy these. Okay, so this is a video, I just grabbed it off of YouTube. Again, we're in the robot kind of question. So we talked about the fact that it's not perfect. Sensing is not perfect, actuation is not perfect. Let me show you, it's a very short clip. Which honestly I don't know where it's from, but that's not quite the intended motion, right? That's not quite what it was supposed to do. So I'm guessing what it had to do was move forward, but the dynamics of it didn't quite work, right? Something happened there with the robot. Now the rest of the clip, it just picks it up and it keeps on going, so it's fine. But so don't feel too bad for it. But the problem here is the task wasn't quite appropriate for the dynamics of the robot, or in this case. So let me give you a another simple example. Let's say my task is I have room 1, I have region 1, region 3, and region 2. And my task is just go between region 1 and region 3 infinitely often. But if you see a pursuer, I want you to go back to region 1 and stay there. So this is an example trajectory. So I'm starting to move towards region 3. Suddenly I see a pursuer. I want to go back to region 1. Pursuer goes away. I'm going to go back to region 3. So this is a reactive task, right? I'm reacting to the environment. This is the state machine that I would get from that. Very, very simple, 4 states. It's kind of hard to see, but it's labeled with the environment. So I'm starting in room 1. This is state number 1. If I don't see a pursuer, I'm going to go to 2. If I don't see a pursuer, I'm going to go to R3. And then back to R2 and R1 and so on. If I'm in R2 and suddenly I do see a pursuer, I want to go back to R1. Perfect. If I have a point robot, x dot equals u, no problem. If I have a robot that has some more interesting dynamics, or has some inertia, or have something that I can't abstract using x dot equals u and a point robot, then I start having problems. The question is, can I actually continuously implement this controller in a guaranteed way? So we've addressed, so my picture is the Create in my lab with kind of the universal gripper on that. So we attack it in 2 ways. I'm going to talk about one way here, which is more of a top-down approach. We've also been looking at the bottom-up approach, but it's under review, so I don't want to talk about that right now. So here's the idea. The idea is, let me assume, the top-down approach says, or what we're saying in the top-down approach is saying, I'm going to assume the robot can do whatever I ask it to do. Let me generate that controller. Let me generate that state machine. Now what I need to do is I need to make sure that I can continuously implement any transition in that state machine, and also that I can always change my mind. So if you look at state 2, I'm going to go, if I'm in state 2, if I don't see a pursuer, I'm going to go to state 3, which is R3. If I do see a pursuer, I'm going to go to state 1. So this state machine is a little bit different from what you usually see, because here, the transitions take time. The transitions are not instantaneous. So I'm spending time in the transition, and if while I'm going from R2 to R3, something changes, I'm switching to a different transition. So to do that, we have the notion of we kind of elaborate on the idea of sequential composition, but by what we're calling reactive composability, so reactive composition. So now it's not enough that the idea of funnels, right? So we have experience with that, right? Instead of having funnels that lead in one to each other, that's fine, but I need to be able at any point within that funnel change to a different funnel as well. So this is what you're seeing right now. What you're seeing right now is the green one. This is xy theta space. This is a slice in theta, so this is xy for the same environment over there. This is one funnel. So at any point to here, I can drive into R2. The problem is if I'm at any point in here and I want to suddenly I see pursuer, I want to be able to switch and go here. And if I can't, I want to be able to give you some feedback about what is the region around R3 in which I'm not allowing you to switch the pursuer. Okay? So in this case, what we did some kind of what we call outgoing funnels. So this is what's going from R2 to R3. But to fill the space, we also consider incoming, not incoming, kind of funnels that lead to funnels within the same region. So all the red funnels are funnels that I can go to a funnel that will lead me out. And then by composing them, depending on what's going on in my environment, then I have those guarantees, because all these are invariant sets. Once I'm in one of these invariant sets, I'm guaranteed, as long as my disturbance is bounded, to follow these funnels into where I want to go. So this is an example. I'm starting here. I'm starting to move along this funnel, this L12. It's kind of hard to see. I'm starting to move. Once I pass from this region to this region, I'm switching funnels. So I'm switching funnels to go into this area. And suddenly I see a pursuer. So I was using this dark green funnel. Suddenly I see a pursuer. I'm switching to this, it's kind of hard to see, but I'm switching to this inward, that's what I was looking for. Inward-facing funnel, which is this red, it's kind of underlying this red, to go back to a funnel that will drive me here. My pursuer turned off, so it got away. And now I'm taking this funnel back into R3. So if I'm able, so this is a very conservative approach. If I'm able to show that these funnels exist, then I'm guaranteed, as long as of course nobody picks up the robot and throws in the garbage, I'm guaranteed that the continuous system actually implements my discrete system, even when it's subject to nonlinearities and all those and disturbances. All right, so I talked quite a lot about what's going on here and what are the unique challenges when you talk about a physical system using these discrete techniques. I want to talk a little bit about the high level, mainly because we have some work. I think it's very, very exciting. Well, I find it very exciting, but it's still kind of work in progress. And I've talked to some of you about the idea of language. So this is what I'd like to write. This is what I need to get. Okay, so I need a logical representation. This is just using the text that we actually put in the controller. So this is what I want. This is what I need. The question is, how do I go between them? So the first thing that we did, and this was kind of really long time ago, 2008, and a little bit in 2010, we said, oh, you know what? I don't know how to do natural language. It's a hard problem. Let me just build a structured English interface. So this is by no means pretty. This is the grammar that we were using. The semantics are very, very clear. So moving between the structured English and the logic is very easy. But then you'll have sentences like, if you're activating spill top, then always not between, or this is kind of the locative prepositions, but I have things that are, it's definitely not natural language. It's much easier to read. It's easier to write. I wouldn't say much, but it's easier to write, but it's not natural language. But this was the first step to allow us to get more and more natural and allow people to write this without actually understanding or knowing how to write logical formulas. What we've done recently, and this is from last year, we've teamed up with NLP people, so Mitch Marcus's group at Penn. And what we did, we really incorporated a natural language pipeline that allows us to go from natural language all the way to the LTL, and from there on, we've got it. So what do we have? We have parsing. So we've used the Bickel parser. So it's a kind of a standard parser, definitely not targeted towards robotic. It's a parser out of Penn. This parsing creates a semantic structure in which we're looking at verbs, and we're using what's called VerbNet, which is a big database that attaches senses to verbs. So, for example, I like this example the most. So, go, visit, I don't know if visit actually, but all the verbs that are synonyms to go, they're all mapped to the sense meander. I believe that's the verb that they're using. But they all have the same meaning. So they all represent the same semantic action, right? So we can use VerbNet to figure out the semantic actions that are of interest, and then we generate LTL. Now, to truth in advertising, going from the semantics, so going from the parsing and to the semantic, that's automated. There's a parser, there's a semantic, we can get VerbNet. Going from the verb census to the LTL, that's currently manually coded. So one thing we want to do is automate that as well, maybe using learning, or we need to think about that. But just to illustrate, if I have a specification that says go to the lounge, I'm going to get a command go, the location is the lounge, and this is the specification. This is what it translates to in the logic. So it's a little more complicated because it actually has to, I need to kind of state that I'm not there right now, or I'm not starting out there, and that I eventually want to be there. So it's a little more, so the mapping between the semantics and the LTL is not trivial, but we want to work on that and kind of look at those things. The nice thing about having the natural language, so this is kind of the work from there. So follow me, don't go into the kitchen. So follow me translates to a lot of logical formulas because it's kind of a very, very high level behavior. So you have to say, if you're here, you need to be here, and so on. It's easily automated. And once we capture what follow me means, it's automatically generated for any new environment. So it's not that I have to, I have a new map, I have to rewrite this. But the initial mapping between the semantics and the LTL requires expert knowledge, if you will. So we're able to do that. The nice thing about the fact that we have a semantic semantic representation, we have the parse tree that we had before. Now this high-level task is decomposed, or this high-level specification is decomposed into a set of subtasks in the logic. And now what we can do is, while the robot is moving, we can query it and ask, what are you doing? And it's not going to tell me, so this is kind of, what are you doing? I'll extend this out. It's not going to tell me I'm following you. It's going to tell me really the subtasks. I'm currently trying to follow the target to hall N. I'm currently trying, and this is at different time steps, of course. I'm currently trying to follow the target to kitchen. Because the language already was decomposed into these subtasks using that. So that's kind of a nice way to give feedback. I told the robot, follow me, and now I'm asking you, what are you doing? I'm following you to kitchen, right? So I can give you a lot more detailed information, more detailed than what you specified to me. That's kind of exciting to us. Okay, so I think this is pretty much covers what I was talking about. The high-level specifications, there are many, especially you guys know that there are a lot of ways to interact with robots, not just programming. There are different modals. We're looking at definitely at language. That's what we're interested in, and we're kind of moving along more towards the NLP side of the world. The verifiable, how to incorporate dynamics, optimality, robustness, scalability. Scalability is an issue. Scalability, how big of a problem can we do? That's always a question. So this is all implemented in LittleMop. It stands for Linear Temporal Logic Mission Planner. It's open source. It's Python-based. If you want to play around with it, absolutely go ahead. It works. I need to remove that. It worked with ROS and Gazebo, but the previous instantiation of Gazebo. So I'm not sure it works with the current Gazebo. So, but it works. It's very easy to extend to different platforms. The idea is you just write kind of something that knows how to talk to something else. This is just a few acknowledgements. These are some of my students. Not all of them are in this picture. Vasu, the one in the middle, she's now at Caltech. Ben on the left is going to be finishing up soon. And yeah, and funding, of course, always important to acknowledge. And that's it. Thank you very much for your attention. Yes?
I have a question.
Yeah.
Just start with the state machine. It seems like to me that one of the advantages of temporal logic was that it was originally designed by linguists for explaining sentences in natural language. But for this problem, it seems like you could skip a step and start with the state machine.
But then I'm putting the burden on the user to be able to specify things in state machines, which I don't know if that's more natural than saying something, than using language for that. So the structured English, I agree that that's not the right level. But I think the right level is language, and the language will map. I don't know how to map language immediately to state machines, because it's basically it's not a path, right? It's a state machine. There are decisions to be made along the way. So the LTL is a kind of an intermediate representation that will allow me to synthesize the state machine. But really, I think the language is the right interface, because I know how to write state machines, and I like writing state machines. I'm sure you know how to write state machines and enjoy that. But I don't think that's a natural way for people to interact. So, but I could be wrong about that. That's yeah.
So kind of in the same vein, have we thought about instead of specifying things through language by demonstrations, and then maybe backing up the LTL representation that always holds for a set of certain demonstrations?
So I'm thinking. So yes and no. Okay. Yes, I want to do that, but one demonstration is not enough. One demonstration shows me a path, shows me a sequence of things. It doesn't show me any decision making, right? Any reaction to the environment. So really, what I need to have is many different tasks. Now, an LTL formula captures infinitely many infinite executions, right? So that's very, very, very rich. So yes, we were interested in looking at that. Yes, we're interested in looking at if I let someone do kind of different behaviors, and for me to understand what it's doing, that is something that we want to do for sure. But it requires a lot of different behaviors for me to capture the richness that can be captured using, because if you're just showing a path, you don't need this stuff, right? So just kind of before I don't know if any more questions, I want to emphasize kind of two things, right? One emphasis is on the verifiable aspect of it. So being able to provide some guarantees, not a guarantee that the robot will never fail, because I don't think that's quite appropriate. But saying nothing is not appropriate either. So you have to be able to say some things about these systems. That's one thing. The other thing, kind of the things I've talked about here, you can sit down and write code for anything that I showed here, and anything that we were talking about. The idea is to push the abstraction up one level and let you talk about the specification, and then have a process that doesn't require a person to write the code and introduce all the errors, all the misconceptions, and all the preconceptions of what should be happening there, and really remove that part of the testing and the human-induced errors that comes when you're implementing code. So it really is pushing the abstraction up one level and reasoning about the specification. So yeah. So, but if your task is go from A to B, you shouldn't use this thing. This is not appropriate. If you want to do complicated things with the robot, then this becomes appropriate. Harry?
So I have a couple of questions. So the first one is, I would imagine like in software engineering, also with medical devices, there are already these systems they have in place to verify, that the device is going to work, or at least not hurt somebody, or the software is going to work. And I really know very little about that world. So I was curious, do you know anything in that world that applies to your world, or is there anything in your world that can apply to that world? For example, with the Da Vinci robot, Andre has worked on this. They want to be able to say, hey, we're not going to kill someone with a robot. So is there any fertilization?
Yeah, so you're asking kind of the verification versus synthesis. So this is more of the synthesis question versus the verification question. So
is there a verification analog in software engineering that applies to you? Is there a verification analog?
So we're doing a little bit of verification by the fact that we're, for the continuous aspect of it, right? So I'm synthesizing a controller, and then I'm verifying that I can actually implement it continuously using these kind of low-level controllers or these funnels, this funnel idea. So that is the verification aspect of this kind of work.
I started working on that in 1981.
Verification of
the software one is much more difficult because of side effects and other things. So one, bad as this thing is, right, in terms of scalability and all that.
So I mean,
software.
I mean, and Andre, other people, but medical devices, you think they'd have software verification tools to verify everything. They don't.
No, they don't.
They want to have it, right? That's kind of what there's a lot of.
What they want.
Yeah, I want it, right?
decision tree, and then if this part fails, what happens, and they
Yeah,
their way down.
So I mean, it's kind of interesting. Kind of this. I was talking to someone about the certification of how does the FDA certify these things. So it's kind of like we show that it's close. So I was talking to I forget a person from a company that does implants for dental implants or robots to do kind of the drilling. And what the FDA wants is basically you tell them that this is close enough to something that you already approved, and let me show you kind of the delta.
That's
right?
something else, but we could say that for.
But
that's a clearance. That's a clearance pathway called the 510K.
Yeah.
But that's different from the failure analysis. That,
Yeah.
But we'll stop there. So I have another question for you, more low-level question.
Yeah.
So I like to think about funnels.
I know.
I copied the idea from my department head.
Yeah. I know.
And in your example, you get this pursuer-evader problem. So this is really a low-level question. So what I was I like the idea of saying, let's just plop. Well, I guess I have two questions. So the first question is, it seems to me that somebody has to hand code where the funnels are going to be in all the examples that you've done.
We sample them.
So you randomly, how do you sample them?
Just randomly. So we use RRTs to sample trajectories. So this is very computationally expensive. So we need to make this prettier in the sense that we should sample more intelligently. But really, we're sampling trajectories, and we're doing kind of optimization to have the rest headrake kind of fitting a funnel around it. So it's automated.
I noticed that all the funnels had smooth boundaries. Is that seemed unlikely to me?
It's the way we design them, right? So the way they're defined, yeah, because it's kind of it's a set of the Lyapunov function, a set of ellipses, right? Basically, it's a set of ellipses over time that kind of build back.
That was just being iconic.
No, those are actually funnels. So I mean, it depends on how you do this, but the specific optimization program that we're doing is looks at ellipses.
The next thing is for this problem we had where the pursuer is going to a corner. I'll draw it here, and then all of a sudden sees the bad guy. Yeah, let's say he's an evader. Sees the evader and then decides to flip on another funnel and then go.
Yeah.
What I was trying to understand is shouldn't you just have a giant prepares graph where you add into the state of that prepare? Maybe this is your question. Where you add into the state the existence of the pursuer at that in the room, and that's what decides what goes into. That's what decides which funnel to activate.
That's kind of what's happening.
Oh, okay, it's not the case that you have a condition that you're checking for, and then when that condition is satisfied, you turn on the funnel. Or is this
So I have a state machine that I'm running, the 4-state machine. Okay. And now I'm saying, okay, my transition that I need to execute is from R1 to R2. So let me go look at the prepares graph and go through those funnels. And now if something changes, I'm going to change my transition. So right now I'm in room 2. Let me figure out in my current position which funnel I'm in, and let me kind of choose one that takes me back to room 1.
Oh, okay. Then let me ask another question. What does a funnel for a pursuer look like? In other words, is the goal set where the evader is?
No. This is not a pursuer evader. So if I wasn't clear about that, so there's an event I detect. Something bad happened. Let me go back to R1. Okay. I don't know where the pursuer is. There's no. It's just the X's I had there were not locations, but time. Yeah, I know. So I probably should use a different word. But the X's that I had there were just instances in time, or where the robot was when it senses this event and it has to go back.
So by the way, I think trying to make the pursuer evader approach work with funnels is actually an interesting question. It's an interesting problem. So
yeah.
I wouldn't back off on that. But that's okay. Well, thank you.
That requires some abstraction, which I'm not quite clear what it would be.
I don't
maybe in the funnel space, right? So having all the, I don't know. That's a good question. Yeah.
It would be interesting.
Yeah.
There's been substantial work on pursuit evasion games, and it's called the differential game.
Mm-hmm.
And I think that Claire Tomlin and Shankar Sastry did some work on that. I don't know if they've done any recent work on it, though.
They had from a couple of years ago, right? So they had.
I thought it was on it one time. Well, I'm old.
No, they did some. So one of Claire's students, they did kind of really nice kind of a game, really capture the flag type thing that they were. That was, I don't know, 2 years ago, 3 years ago. Yeah. I'm gonna ignore Howie.
In certain cases, like you're not putting any constraints on the environment. What I mean is that,
I am, actually. So I'm making some assumptions about the environment. I could make some assumptions about the environment.
Specify, for example, if the electricity goes off, okay, everywhere is dark, not just this place. So it's a condition. Can you put this into your environment definition? Because like as it is, the robot is assuming that anything can happen in the environment, which can be huge.
Yeah.
As you know, there we have a lot of real constraints. If I have a single projector in the whole building, it's either here or there, and then that's it.
So I can always put constraints on. You're absolutely right. So I can always put constraints about. So I need to abstract my environment to see what events are of interest. So if I need to know that there's no electricity, I need to put that into my list of propositions, if you will, and then I can put constraints on it. If I don't put any constraints, my state space is very, very big, and I might not be able to. It might be unrealizable just because the environment can do something to make me fail. If I put constraints on it, then I'm expecting it to. I'm expecting my task to. I'm expecting the robot when it's executing that those constraints will actually be met. If the constraints are not met, I have no guarantees about the robot. Now, the only caveat to that, or the extension to that, is we've done recent work in which we create a controller that still tries to make progress towards its own goals, even if the environment violates its assumptions. So if you have, I mean, sometimes you can't, right? If you tell me that one of these doors is going to be open, and I need to get out, and both doors are closed, I can't get out, right? But if I'm already out, then I don't care that both doors are closed. So we have some work on that, how to add kind of a recovery from environment violations. But I can't assume things.
But you're not keeping them separate. Like I assume that, the environment constraints and the task specification could be different because
they are separate actually. I'm treating them. I mean, they influence each other, right? So I need to know. But yeah, they are separate. So and I don't have to assume anything about the environment. But then my state space is much larger, and it might be unrealizable because it can do something. Yeah, absolutely. Yeah.
So you mentioned like scalability. Like how do you have have you quantified like exactly how many states and
it's a very good question.
Transitions and things you have, because like I guess humans clearly are not like verifiable, right? So like because we have a ridiculously large state space and a ridiculously large number of actions. So maybe it's the probability way to go.
Yeah. Well, so in terms of scalability, so I have a pretty not great answer for you. We're able to synthesize state machines that have 50,000 states. The reason I'm not putting that as the actual number is because we're doing something stupid. We're actually extracting, so this is all represented symbolically, and definitely with BDDs that kind of came out of here, right? And what we're doing, we're extracting the explicit state, and that's the bottleneck of our approach right now. That's where because it becomes huge in memory, and that makes all the malloc errors and all that. We are working right now, and just in terms of we need to implement it. Because, one of the things that you never get to is just leaving everything symbolic, and then I'll have a better grasp of. But then it would be much larger. But still, yeah, absolutely, there's a scalability issue because your state space grows exponentially with the number of environment propositions. So the more information I need about the environment, and if it's independent, right, then it goes exponentially. And then you have to start thinking about maybe hierarchical approaches, and then you have to think about maybe decomposing the task and then verifying the composition, which is a hard thing to do as well, and all these things. So I don't have a good answer for the scalability, but the 50,000 is not the bottleneck. But that's what we're able to do right now. Thanks.
You mentioned using feedback to improve the likelihood of reaching the goal and succeeding with the task. Could you talk a little bit more about what that looks like specifically, especially where are those suggestions drawn from?
So yeah, so what we're able to do is basically we actually give you a formula, a new formula that says this is a safety. Always not door one, or always not go through door one. We're actually providing you with snippets or these specifications, additional specifications, and you choose whether you want to. And we're currently doing it in the logic, but we could map it very easily to language, or to some structured language. But yeah, those are the kind of things. Or when we limit the set of initial conditions, we say not this set, and we can give you a set represented using the propositions. That's the idea. Yeah, not non-language yet, but I mean, moving to language would be very easy. Kind of a very simple, generative, not pretty, but understandable. Yeah.
Do you have any more questions for our speaker? She has some time left. All right, well, let's thank her once again.
Thank you.